Okay. All right. Welcome, class. Due to the coronavirus, this isn't exactly the most ideal scenario, but gotta learn. I'm thankful for each of you guys tuning in and watching. As always, have questions, just send me an email. I'll be pretty available for connection. A couple things. I'm going to go probably a little bit faster here, just because you guys can pause, rewind, do all that stuff. If you have questions, I encourage you to take all these good notes, and let's just rock and roll right into Pre-Calc, Chapter 10, Section 4, Mathematical Induction. If you brought your books home like you were supposed to over the break, you can follow along on page 621. I'm going to reference my notes here every once in a while, just so I don't make a mistake, as I've already made plenty. This is my second recording of the video, because clearly I'm a YouTuber, not a math teacher. So, first thing is, we must start with, what is mathematical induction? Well, mathematical induction is a three-step process, but it's most specifically, it's a type of proof. Remember, we did proofs way back 2 years ago, back when I had you guys for geometry. So it's one of those things, except for in this case, like I said, there's 3 steps. You have your first step, which is called your anchor step. So you have to prove that the base case works, which, as I said, is called the anchor step. Often, that'll be something like our n equals 1, where n's are obviously our number of terms in that sequence, and it's just that first step, that equals 1 case. Okay. Later, or next, you have to do a hypothetical step. So prove a hypothetical step. Where I don't really know where I'm at in the chain, so we'll just say that that is our n equals k, and that is just called the hypothetical induction step. Hypothetical induction step. The third and final step is we have to prove what's called the induction case. Induction case. It's essentially called the next step. I'll have in parentheses. Its official term is, again, the induction step. And where our hypothetical was n equals k, our induction step is n equals k plus 1, because it's just the step after the hypothetical. It's that next case. I'm just adding 1 to the number of steps that I've taken. Okay, so that's all mathematical induction is. We get 3 steps. Now the thing is, our base case often works by itself, but these two will often work in tandem together. You use some. They will, like I said, work together, often through algebra. I can already tell I'm already starting to do that thing that bugs you guys where I lean. I apologize. 6'5", too big. I just need to do a better job. I apologize. So that is what mathematical induction is. It's a 3-step process of solving these problems. Now that kind of seems kind of messy and kind of complicated. So the easiest way I can explain mathematical induction is it's a giant ladder. So on our ladder, we have 2 steps, or we have 2 bars connected by a series of rungs, where the bars are just my sequence, or my series, and the bars are my steps, or my number of terms. So like I said, we have that first step, that n equals 1, that's our anchor. We have to start somewhere, and that helps keep us grounded. If I can't take that first step on that ladder, I can't progress. Then, as we said, we get our hypothetical somewhere. Our hypothetical n equals k. K is just some variable, meaning I don't know which term it is. I can't say n equals 4 because it might not be. It could be our second term right after my anchor. It could be my third. It could be my 2000th. We don't really know. So we have to prove for every possible situation for our hypothetical. And then finally, we also have to do that inductive step. Inductive, where, as we said, n equals k plus 1. So if k was 6, my inductive would be the 7th rung, etc. By proving every single potential case works, and every case works after that, I can prove that the entire chain would work on an infinite ladder. Okay. So now we're going to get into the meat and potatoes. We just got 3 examples to work through. Our first one, let's see, example 1, we're going to prove a summation. I know Caden wants to think of that sigma, and you could essentially treat a summation. What I'm talking about is essentially a series from 10-1 or 10-2 or 10-3, where we just add up all the terms. Okay, so prove a series. So we need something to prove. So prove that 2 plus 4 plus 6 plus plus 2 times n equals n squared plus n. Often, when we get something like this laid out, first we need to verify that there's a pattern. Each term is being multiplied by 2, right? If my first term, 1 times 2 would give me 2. Second term, 2 times 2 would give me 4. And my third term, 3 times 2 would give me 6. Etc., etc., and that will work for all n. That's why we end with 2n, because we don't know where we're going to stop. Now I just get, inversely, I get n squared plus n. Now often, these guys will have a set restriction. Now we're going to use the same restriction the entire lesson here, where we have for all positive integers. Now positive integers obviously being 1, where it starts, and wherever it ends. Well, we couldn't use 0 because, again, 0 is not positive. It has no polarity of positive or negative, and it wouldn't hold anyway. 0 times 2 would give me 0, but I don't have a 0th term, just like I don't have a -1 term, and etc., and etc. And it wouldn't even work because 2 times -1 would be -2. -1 squared would be 1 plus 1, so we'd get -2 equals +2, which is clearly equals 0, which isn't true. So, again, our 3-step process. First step, anchor. We need to know that n equals 1. So if I plug in 1 to both sides, I get 2 times 1, which is my first term, so 2, equals my 1 squared plus 1. 1 squared is 1, 1 plus 1 is 2. Does 2 equal 2? Yes, so my anchor step holds. Okay. Now we need to do our hypothetical. We get our n equals k case. So, do I know where k is? Unfortunately not, so I have to include everything up to potentially k. So I get 2 plus 4 plus 6 plus plus 2k equals, and again I'm just plugging in k for n, so I get k squared plus k. And there's not really a lot I can do with that algebra quite yet, so I'm just going to hold off for it for now. Like I said, the 2 and 3 steps work together, so we kind of just want to establish them first and then see what kind of algebra we can do. So our third step we get is our n equals k plus 1. So 2 plus 4 plus 6 plus plus 2k plus 2 parentheses k plus 1, because it's just, again, extending the pattern by 1 equals our k plus 1 squared plus k plus 1. Again, sorry I kind of cut off on the board. All I'm doing is plugging k plus 1 into my original formula there. Now it's kind of hard to see where I'm going to end up going with these two, but I need to make sure that somehow I can meet them in the middle, which is through algebra. So, let's see, first thing we can do is we can just do some algebra to see what kind of figure out what k plus 1 squared is. So I get k plus 1 squared, so k plus 1 times k plus 1. Well, k times k, that's going to be k squared. K times 1 times k, that's going to be 2k. And then 1 times 1 is going to be plus 1. And I still have my plus k plus 1 out here. Plus k plus 1. And I didn't do anything to this side. We can just distribute this too, right? So I get 2, 4, 6, etc. 2k plus 2k plus 2. So this equals 2 plus 4 plus 6 plus dot 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 plus 2k plus 2k plus 2. Shoot, should have planned that a little better. Let's see. 2 plus 4 plus 6 plus dot 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 plus 2k plus 2k plus 2 equals k squared plus 2k plus 1 plus k plus 1. Okay, again, a little crooked, I apologize. Now, with all that being said, we already established that this entire expression equals k squared plus k. So if they're equivalent, I subtract from both sides. Am I really changing the integrity of the equal sign? No, I'm not. They're the same value. So I can subtract this entire term if I subtract k squared plus k on the other side. So k squared plus k. So all I'm left with is this 2k plus 2 on that left-hand side. And all I'm left on this right side is 2k plus 1 plus 1. Obviously combined terms, 2k plus 2 equals 2k plus 2. Here's some clever little algebra there. Show that 2k plus 2 equals 2k plus 2. Is that true? Naturally. Is that always going to be true? Of course, no matter what k is, especially if k has to be a positive integer. So I just showed that these two steps work hand in hand to prove this for any case. Because, again, I don't know what k is, but it doesn't matter. So, again, example 1, prove summation. Okay, moving on to example 2. We're going to prove divisibility. So, if I say some expression like 3n minus 1 is divisible by 2 for all n that are positive integers, how would I go about proving that? Well, again, I would always start with my base case. So my n equals 1, because this is the easiest case. Again, it's my smallest positive integer, so it's just easy. Don't make things too hard. 3 to the power of 1 minus 1. Well, 3 to the power of 1 is just 3. Minus 1 gives me 2. Is 2 divisible by 2? Naturally. 2 divisible by 2. 2 divided by 2 is 1. That's a whole number. Therefore, it is, again, divisible by 2. So the base case holds. Okay. Now this idea of divisible by 2 just means some even number. Now I'm going to tweak that a little bit, but hopefully you see why. I'm going to say divisible by 2. I'm just going to say that that is 2r. Now I just picked r randomly. It doesn't matter which letter. If you wanted a z, if you wanted a q, that's fine. I just picked r, where r is just some number. Because if 2r is an expression, naturally it's divisible by 2, right? What's 2r divided by 2? Well, just r, so it's still divisible by 2, it's a whole number. Okay, where r is a whole number, I guess it's specified by that, whole positive number. So I can rewrite this expression, again, my second step is my hypothetical, where n equals k. So again, 3k minus 1, and again, it has to equal something that's divisible by 2, so let's say equals 2r. By taking that same logic, I have to write my third step, n equals k plus 1, so I get this idea that 3 to the power of k plus 1 minus 1 equals 2r. Again, I just replaced my n with k plus 1, so that means that the k plus 1 has to be the exponent. So I'm actually going to take a slight little detour over here and talk about how we can compare these. So first, let's talk about this. If I have 4 squared and I multiply it by 4, I would get 64. I would get 16 times 4, right? I can rewrite this as 4 squared, that's just 4 times 4 times 4. So I have 3 4s, right? That's the same thing as 4 to the power of 3, which again is 64. But let's take it one step in a different direction. I can rewrite my original expression as 4 squared times 4 to the power of 1. Because again, anything's to the power of 1, power of 1 doesn't change the integrity of it. The power rule for exponents says that if I multiply by something with the same base, all I have to do is add exponents. So again, that's the same thing as 4 to the power of 2 plus 1, or as we said earlier, 4 to the power of 3, which just means 64. So if I multiply by the same base, multiply by the base, I can add 1 to exponent. Okay. Just some little algebra wrinkle that I'm going to throw in there. Okay. So I'm going to start with my middle column and work my way hopefully to this purple column. Now, to start with that, I want to get my base by itself, so I'm just going to add each side by 1. Excuse me. So I get 3 to the power of k equals 2r plus 1. And like I said, I don't want 3 to the power of k in my third expression. I want 3 to the power of k plus 1. So I'm going to multiply by that same base number to hopefully that situation holds. So I'm going to multiply this side by 3. Now it's an equal sign, so if I multiply one side by 3, I have to do the exact same to the other side. That's that multiplication identity. Multiply by 3, identity, multiplicative property of equality. So 3 to the power of k times 3. Again, as we said over here, I can just add that 1 to the exponent. So 3 to the power of k plus 1. 3 times 2r, well that's just going to be 6r. And 3 times 1 is going to give me plus 3. Okay. My final question here is, did I just have 3k plus 1 by itself? No, I had 3k minus 1. So I need to get a minus 1 over here, so I can take 1 away from 3. I can subtract 1 from both sides, again the subtraction property of equality. So I get 3 to the power of k plus 1 minus 1 equals 6r plus 2. Now, I get 6r plus 2, and I really need to make sure it's divisible by 2. Is there any way I can show that it's divisible by 2? Well, what number exists in both these that I can factor it out? What number exists in 6 and 2 that I can factor out? Well, 2 does. If I divide each by 2, so 6r divided by 2 gives me 3r. 2 divided by 2 gives me a 1. Okay. So here I'm given 3 to the power of k plus 1 minus 1 equals 2 parentheses 3r plus 1. So I get this 2 times this quantity of 3r plus 1. It's not exactly the same thing as just r. Now, I grant you. But, does it matter? Because all we need to make sure that it's divisible by 2. No matter what my r is, especially if it falls in the rules of positive integers, is it going to matter what my r is and my expression is in here? Let's say r was, I don't know, 4. 3 times 4, 12, plus 1, well that's going to be 13. 13 times 2, 26. See, and 26 is obviously divisible by 2. No matter what my r is, I always have to multiply by 2 at the end, which means that I'm going to get a number that's divisible by 2. So, this holds. Again, not exactly, that's a little tricky. They aren't exact, but they are essentially equivalent in the grand scheme of things. Okay, so that was example 2, proving divisibility. Now, example 3 will be the last one that we talk about here in this video. We're going to prove an inequality. We're going to prove that n has to be less than 2 to the power of n. Again, for all positive integers. I cannot stress that enough. These rules have to be followed. So, first we always start with our anchor, our base case. So I get our n equals 1. So again, 1 less than 2 to the power of 1. Well, 2 to the power of 1 is 2. Is 1 less than 2? Yes. So our anchor has to hold. Okay. Now we can move on to our other steps. 2, we get n equals k, our hypothetical case. So I get k is less than 2 to the power of k. And I can't do anything with it just yet. Let me clean that up a little bit. And then third, we get our n equals k plus 1. So I get k plus 1 has to be less than 2 to the power of k plus 1. Alright. So again, building from a middle to my right, let's see. Again, using the same logic as we said before, I don't have a 2k, I have a 2k plus 1. So I have to do what to both those sides? Well, I got to multiply by the base number that I have there, so I can add one to the exponents of 2. So I get 2 times k, so 2k, less than 2 to the power of k plus 1. Unfortunately, there doesn't seem to be a lot I can do with that at this point in time. So I'm just going to hold on to it for now. So I'm going to figure out something else I can really work with to sort of get this k plus 1 piece. Because I have the right side, but 2k is the same thing as k plus 1. That only works in, what, just the 1 case? It wouldn't work in the 2 case, for example. So let's think about this. All positive integers. Well, that means that k has to be greater than 1. It's all the other positive ones. I've already used 1, so all my other k's have to be something else. It have to be greater than 1. Well, I could subtract 1, so k minus 1 is greater than 0. Well, that's not exactly what I wanted. I wanted k plus 1, not k minus 1. That's not really getting me anywhere. And what's this deal with this 2k? Well, let's try to get something where I can compare it to. Here I have a single k, but if I got a 2k, I can sort of compare it and bridge the gap through an inequality process. So k really does equal 2k minus 1k, right? If I have 2 apples, I take away 1 apple, I still have 1 apple. So this idea that k equals 2k minus k, well, I can just plug that in, so I get 2k minus k, and I haven't done anything with negative 1 yet, so I'm going to keep that, minus 1 greater than 0. Well, that seems kind of messy too. I haven't really gotten anywhere with it. I still have I have my 2k, but now I have a negative k minus 1 and not a k plus 1. Well, I were to add a k and add 1 and send it to the other side, plus k plus 1. So now I have 2k has to be greater than k plus 1. Okay. Now I have a 2k, I have a k plus 1, and I have a 2k plus 1 and 2k plus 1. I have all these pieces, but how do they interconnect? Well, let's start with my expression over here. 2k is less than 2 to the power of k plus 1. Now, relating it to this, it says that 2k is greater than k plus 1. Okay, so 2k has to be greater than k plus 1. Well, if I had an expression like 4 is less than 5, which is less than 6, do I really need this 5 there to show you that 4 is less than 6? No, if 4 is less than 5 and 5 is less than 6, 4 has to be less than 6. So I can just jump right to 4 is less than 6, right? That stuff holds. So do I really need this little 2k part anymore? Because all I need to show is this. So I don't actually need my 2k anymore. So k plus 1 has to be less than 2 to the power of k plus 1. So that would prove that type of inequality. Okay, those are all the notes over the section that we're going to go through here. I might change the homework assignment. I got to go through and look at it and tweak it. I might add or subtract problems based on these present circumstances. I just wanted to wish you guys all well and hope you guys are all stay healthy and your families stay healthy. There's no concern. There's all this media attention and stuff just freaking everybody out. I just hope you guys relax and everyone's all good. If you have any questions over any of this, over the homework that I'll send out via email, let me know. And I just wish you guys all a happy-ish, school-free